Welcome to part 3 of multidimensional essentials. In this section, we're going to talk about Platonic solids, the polyhedra, the three-dimensional shapes that define the shape of space itself. So Buckminster Fuller tells us, well, okay, really it's Amy Edmondson. She studied with Buckminster Fuller for a long time, and we looked at this book, Synergetics, this weighty tome, which says ridiculous things like, in a radiational or gravitational wave system, fourth powering is identified with the interpointal domain volumes. It is not possible to demonstrate the fourth dimension with 90-degree models. Regular tetrahedron, blah, 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 right? So it talks like that. And so thank goodness for this woman, Amy Edmondson, who was his student, and she wrote a book called A Fuller Explanation. And it's basically the Cliff's Notes, or like the Reader's Digest guide. So I like to sit there with A Fuller Explanation and Synergetics open, and this is like my Friday night. It's really fun, and go back and forth because she's got all the references and she explains it in English. And so Edmondson tells us the Platonic polyhedra, the Platonic solids, as their name suggests, have been documented by humanity for at least 2 millennium. They're going to be named after Plato. Plato was talking about them. So that's at least 2 millennia. Fuller's definition is that every polyhedron is a system dividing universe into 2 parts, inside and outside. And this is what we've just been talking about, where for me, there's an inside and there's an outside. There's me and the world. And this is what makes the ego thought, the I am, a system. I'm a complete system because I'm me, and then there's the world outside. And so this is what these Platonic solids do for us. So despite the fact that these 5 shapes have been known and understood for millennia, very few people are aware of what exactly defines this group and what are the implications for space itself. So that's what we're going to get into. Now, to define the Platonic solids, the requirements seem lenient at first. There are only 2 requirements. The faces of a polyhedron must be identical. So we look at these shapes. Every face of the tetrahedron is a triangle. Same is true for the octahedron and icosahedron. Every face is an equilateral triangle. For the dodecahedron, every face is the same pentagon. And for a cube, it's a square. So the faces of a polyhedron must be identical, and the same number of them must meet at each vertex. So wherever there's a point, there have to be the same number of shapes connecting at that point. So like with the cube is sort of the simplest example. There are 3 squares that meet at every corner of the cube, right? There's not one corner that has 4 squares connected to it, right? Same with the dodecahedron. There's 3 pentagons that meet at every corner, and it wouldn't work in any other way. So we're gonna go deep into this. We're gonna spend the next 30 minutes or so talking about these shapes. We're getting a little bit into the nitty-gritty of the geometry here. Okay, so the minimum polygon. So let's just be really clear about the difference between a polygon and a polyhedra, right? Polygon is a 2-dimensional shape, a triangle, for example. Polyhedra is the 3-dimensional shape, the tetrahedron, for example, right? So polygon, the minimum polygon is a triangle. We talked about this earlier. The simplest, most efficient way to enclose area is with a triangle. So 3 triangles around 1 vertex form a pyramid, the base of which is automatically another triangle, right? So this is our tetrahedron in over here, right? So if you take the minimum polygon, the triangle, and start putting them together, the simplest shape is this tetrahedron. In one step, you just you put 3 triangles together, and boom, you've got this type of a pyramid. Amazing. So there's our tetrahedron in the upper left corner. The natural next step, okay, we'd put 3 triangles together. What if we put 4 triangles together? And this is our octahedron, right? So the first part, if we put 4 triangles together, they're meeting at that vertex, that only satisfies half of our requirements for the Platonic solid. And so if there are 4 points meeting right here, there must also be four polygons meeting right here and right here and right here and right here. And so in order for there to be 4 lines in there, we add these lines, but then each face has to be the same. And so we just sort of link all those together in the center here. And here we have the octahedron, which is that more traditional 4-sided pyramid, or base of 4 pyramid, and then bottom to bottom, right? Upwards, downwards. This is our octahedron. So great, we're flying right along. We're just stacking triangles together. And okay, what's next? We use 3 triangles, we use 4 triangles, let's try 5 triangles. And sure enough, here's this icosahedron where we put 5 triangles together and they create this little cap. And if we just follow the procedure and just keep adding triangles, we end up with this icosahedron. Icosa meaning 20. Is that true? Yeah. So that's our process for building these structures. Okay, so we went 3, 4, 5. Let's try 6. Oh, but if we're using equilateral triangles, each angle of an equilateral triangle is 60 degrees. And if we use 6 of them, 6 times 60 is 360 degrees. And that gives us a flat plane. That gives us a flat, the 360 degrees is a circle, right? And so we cannot enclose any volume with a circle because it's just all flat. Does that make sense? It takes a little bit of geometric practice. And so one of the homework assignments, one of the suggestions for an activity is to get a pen and paper and draw this out for yourself. I'll tell you that it lands in a totally different way when you are drawing it out yourself and doing this experiment. And it can be really helpful to draw out some equilateral triangles, to actually cut out some equilateral triangles, cut out a collection of them, and then play with them. It's because again, we're dealing with 3-dimensional space, and so you can play with them and tape them together, however works for you. But it really, you can do the experiment with the 6 triangles and see that it creates a flat plane. And so if you can't bend it around to enclose volume, then it's not going to be a polyhedron and it's not a Platonic solid. So we found our upper limit, right? We have a lower limit of 3 triangles that can, or a lower limit of 4 triangles really, or 3 vertices, right? The tetrahedron has 3 triangles at every vertices. So that's our lower limit. And so our upper limit for triangles is 5. Very limited. So that's it for triangles. That's all we can do. So let's try a different shape. Let's try the cube. And okay, so we're just following our procedure. We're taking the square and smashing it together. And so, so we went from the triangle's a 3-sided shape. Let's go to our 4-sided shape. Okay, 4-sided shape is a square. Let's start putting squares together. Sure enough, we've got a cube. Simple. Really, a cube is really easy in a lot of ways. And that's why we use it so much and have like based our whole society around cubes in a lot of ways. Like, we live in a world of boxes, don't we? A bunch of right angles. The cube is inevitable, right? There is no other possibility. Edmondson writes, if there are 3 squares around one corner, the same must be true of all corners. And as before, the structure is self-determining. Again, like, we're not making very many choices here. We're just trying to like structure something in space, and the actual structure of space itself defines what we're capable of doing. And so this isn't arbitrary. This isn't just like, oh, I want to do this. Like, no, like to meet the rules, that is the only thing possible. Okay, so we did our 3-sided shape. We did our 4-sided shape. Let's go to our 5-sided shape. This is a pentagon. And so 3 of them around one vertices works. And if, again, just follow our procedure, this gives us a dodecahedron. Eventually they all connect and enclose the volume of a dodecahedron. And so a pentagon has an internal angle of 108 degrees. So 3 of them works, right? That gives us a total of 324 degrees, which gives us the convex structure that allows us to build a more or less spherical object, right? That allows us to enclose area. But if we try to use 4 dodecahedra, 4 times 108 gives us what, 432, which doesn't work. We can't actually get them all together. And so this is just gives us a hint that 2-dimensional space has qualities just the same way that 3-dimensional space does. So the same rules that limit movement and structure in 3-dimensional space also apply in 2-dimensional space. So yes. Okay, so we did 3-sided shape, 4-sided shape, 5-sided shape. Let's go to a 6-sided shape, which is the hexagon, honeycomb structure, right? And I don't have an image for this, but it doesn't work. It just doesn't work. You try to put it together and it creates nothing but flat planes, because again, a 6-sided shape, those internal angles are, let's see, hexagons have 120-degree internal angles. And so you put 3 of them together and great, you've got 360 degrees. And you cannot do it in a way that doesn't create a flat plane, which is why we use hexagons for, it's so common, like bathroom tiling, right? It creates a flat plane. And so already we've reached the upper limit. So we can only use, to satisfy these really simple rules, there are only these shapes. There's only these 5 shapes that satisfy the conditions. And so this gives us really powerful orientation to the structure of space itself. Okay, did everybody follow that more or less? Yeah, seeing some nods.
I forget which one created 432.
That is the dodecahedron.
And isn't 432 hertz a special number?
It's a harmonic number for sure.
Yeah.
Yeah. So
it's not a Platonic solid, but that combination or that shape repeated does create something special.
Yeah. And so the mathematical and geometrical synchronicities, like it feels like magic because it becomes inevitable, right? And it's like like a sonnet has a very specific structure, right? And at first that feels limiting, and to try to squeeze what you're trying to say into a sonnet, but once you become fluent with the structure actually suggests the next perfect word, where you might not have thought of this word, oh, but it has to be this many syllables and it has to rhyme with that. Well, boom, oh, there's the perfect word for it. And so the math of geometry works just the same way, where we'll get to the musical aspect of this.
Cymatics.
Right. When we get to cymatics, we're talking about music. And I think it was Goethe who said, geometry is just frozen music. Maybe he said architecture is just frozen music, but architecture is just geometry. And that is very, very true. So geometry as frozen music. We see how, oh, the pentagon gets us that 432 hertz, and it's a whole thing.